Okay, question 9, we've got stopping distance, braking distance, thinking distance. So we've got a speed limit sign from a European motorway, and we can see we've got 130 and 110 when it's raining. The sign tells the drivers to drive at a slower speed when it's wet. Why is it safer? So in wet weather or wet roads have less friction, so the braking distance will increase. Now I could have said stopping distance. What you couldn't have said is don't say the thinking distance. This is to do, so definitely not that one. Okay, so it's a nice easy question. Wet roads have less friction, so the braking distance, and therefore because braking distance is part of stopping distance, or stopping distance will increase. I just stick to the braking distance. Show that a speed of 31 meters per second is less than a speed of 130. So I've got my little cheaty way that I showed you. Remember the number 3.6. Once you've got the number 3.6, which is your multiplier, just understand that kilometers per hour is bigger than meters per second. So let's change. Take the 130, divide it by 3.6, I got 36.1, and 31 is less than 36. There we go. So, or I could do the other one. Let's show 130 kilometers per hour, show them on top of each other. Top one, I've got to change to meters, so times 1,000. The bottom one, I've got to times by 3,600, that should say. You can see I've got it right on the next one. So 130,000 divided by 3,600 is 36, and that is more than 31. Next one, the driver's reaction time is the time between the driver seeing an emergency and starting to brake. So it's at 31 meters per second. It travels 46 meters before they see the emergency. Calculate the driver's reaction time. And we've got to do it to two significant figures. So we're going to need our shoot Donald Trump. We're after the reaction time. So reaction time equals distance over speed. We're working at that. Go into the question. There's the distance, 46. There's the speed, 31. And we've worked out it's 1.48, which we would now need to go to 1.5 seconds. Next one, we've got a velocity time graph, and it's on the track for 7 seconds. Use the information, describe when and how the velocity and acceleration change. So we can see we're accelerating here, constant speed here, we're decelerating here, and we're decelerating here, and this deceleration is greater than that deceleration. So there's the basics. We speed up, we go at the same speed, and then we start to slow down until we reach zero velocity at the end, where we come to a stop. So to put that in, but just remember, use between. So it's at the different times. So we've got to refer to that. So we can just go through, let's do 0 to 2. So between 0 to 2 seconds, the train accelerates at a constant rate. It's a straight line. Between 2 to 4.6 seconds, the train stays at a constant speed. There's no value there, so I can't read that off. If there was a value there, I would use that value, whatever it was, 20 meters per second. The next part, between 4.6 to 5, the train decelerates at a constant rate. And now we're just going to do with our last part, where we're going to finish with the 5 to 6 section. Between 5 to 6, the train decelerates at a constant rate, which is lower than it was between 4.6 to 5 seconds. And if I wanted to, I could add in here, and at 6 seconds, it has stopped, or it is stationary. So just, that is your best friend, using the word between. Between. And that's it.